Hello and welcome to this video lecture in the course for Secure Systems Engineering. In this particular video lecture, we will be looking at a brief introduction to side channel analysis. So, this video lecture assumes that you have a decent background about the AES block cipher, and you also know a little bit about the RSA public key crypto system. So, what we will see in this lecture is how we could use a few tricks to break these extremely strong algorithms. To actually start off with, the modern block ciphers are designed with very strong assumptions. So, they are in fact designed with the assumption that an attacker could know everything about the algorithm except the secret key. For instance, the attacker would know the entire encryption algorithm, the entire decryption algorithm, and we also assume at the design time, the attacker would be able to determine what the plain text is and the corresponding cipher text. Stronger assumptions are also done where we make the assumption that the attacker also can choose the plain text that he wants to encrypt, or in other circumstances choose the cipher text that he wants to decrypt. The only thing that is unknown in all of this is the secret key. Now, the goal of the attacker over here is to be able to manipulate the plain text, cipher text, choose different plain text, choose different cipher text with the objective of identifying what the secret key is. The whole idea is that if the secret key is determined, then subsequent cipher texts based on that algorithm and that specific secret key can be easily decrypted. Why exactly do we make such an assumption? So, we make these assumptions because it's very difficult to keep things secret. So, we want to actually minimize the amount of information that is kept secret. For example, if we use an encryption or a decryption algorithm and we assume that the attacker does not know about this algorithm, and we base our entire security on this particular assumption, it may be possible that attackers actually learn about this algorithm and how it actually functions, or is able to actually reverse engineer the specific algorithm. An interesting case study is about the two stream ciphers A51 and A52, which were initially kept secret. Now, so various researchers have figured out how A51 and A52, there was a combination of leaked information about this algorithm plus reverse engineering, and eventually after a few years the attackers were able to identify how exactly these algorithms function, and they were being able to create cryptanalytic attacks which can break these algorithms. So, this was in the late 90s and early 2000s where both A51 and A52 were actually broken, and it eventually resulted in a new cipher known as the A53 that was designed. Now, all ciphers that we use today in practice are designed with this assumption. So, ciphers such as the AES, RSA, A53 and so on are designed with the assumption that the attacker knows the complete algorithm for encryption, decryption, and can choose plain text and cipher text, and the only secret is the secret key. In spite of all of these assumptions, these ciphers are designed in such a way that any attack would be extremely inefficient to develop. However, what we will see today is that security is as strong as its weakest link. So, we see that it may not be always required for attackers to break the algorithms, but just find one weak link in the entire system and utilize that particular weak link to break the cipher. So, the weak link that we actually look is known as side channels. So, as we see in this very common figure is that if an attacker cannot go through the right way, then what he could possibly use is a side channel and use some indirect information to actually break the specific cipher. So, we will take a small example of what a side channel attack is in a very abstract way. A side channel not only targets the algorithm that is used for encryption or decryption, but also targets the implementation of that particular algorithm. So, for example, if we consider two people, Alice and Bob, and they are using a specific encryption algorithm to communicate with each other. What a side channel attacker would use is the implementation of that particular algorithm. This is due to the fact that this is, for example, let us say that Alice is using a mobile phone like this to speak to Bob. So, a side channel attacker would keep track of the side channel information that is leaking from this particular device. Using this side channel information, the attacker would be able to identify the secret key that was used in the communication between Alice and Bob. So, over the last 20 to 25 years, there have been a large number of different side channels that have been used to break cryptographic ciphers. So, most common ones of them are power consumption, that is an attacker, if he has possession of this particular device or is able to gather the power consumed by that device, then the attacker would be able to gain information about the computations that that device performs. The basic fact over here is that the power consumed by this particular device is correlated with the operations that the device does. So, for example, some operations, say a load instruction or a store instruction, would take considerably more power compared to other instructions such as a simple move or an addition and so on. Other side channels which are very popular are radiation based side channels as well as execution time. So, we had seen such a side channel in a previous video, where we seen how a cryptographic cipher can be broken by monitoring the execution time for that particular cipher. So, in today's video lecture, we will be looking at another form of a side channel attack known as a fault attack. So, here is a very simple example of how a fault attack would look like. So, we have Alice who wants to encrypt this message attack at dawn. So, she is using a particular encryption algorithm whose secret key is 00111. Now, this encryption algorithm is executing on a device like this, and this device would essentially use the message which Alice wants to encrypt and the corresponding secret key and pass it to an implementation of this encryption algorithm. Now, as this implementation is executing within this device, we have an attacker who is monitoring the device side channel. So, in this particular case, the attacker, we assume, has used an antenna or has been able to tap into the power consumed by this device and monitor dynamically the radiation or other side channels such as the power consumed by this device. So, for example, over here, this particular part of this figure shows dynamically the radiation from this device. So, what we see over here is that the radiation differs depending on what bit of the secret key is being executed. So, if you see, look at this part of this waveform and compare it with this part, what we see is that the glitches are very thin over here, while over here we have longer glitches. By using this fact, the attacker could monitor or distinguish between a 0 that is being used in the secret key and a 1 that is being used. Thus, just by monitoring this particular device radiation, an attacker would be able to identify whether a key bit was 0 or a key bit is 1. This is known as a simple power attack and was actually demonstrated in the mid 90s. And since then, there have been a lot of different countermeasures for this specific attack, and also popular devices like the ones we see today can easily prevent such an attack. However, there have been many more sophisticated attacks which are far more difficult to actually prevent. There are different types of side channel attacks. Some are non-invasive, like the power, electromagnetic radiation, and the timing attacks are all examples of non-invasive passive attacks. So, these attacks are passive because the attacker is passively monitoring the side channels that are emitted from the device. On the other hand, the attacks that we would actually look at today are known as non-invasive active attacks. So, these attacks, popularly known as fault attacks, would modify the device functionality in order to glean secret information. So, these attacks are what we are going to look at in this video lecture. So, let us look at what fault injection attacks are. So, just to give a brief background, fault injection attacks are active attacks where faults are induced in a device while it is actually computing a cryptographic function. For example, while an encryption is being executed by the device, an attacker would induce a fault into the device and manipulate the device operation. What would happen when the fault is injected is that a certain paths during the execution would get modified or skipped, and as a result the output from the encryption or the decryption would be incorrect. Now, the attacker would then use this incorrect output to gain secret information about the secret key. So, this attack was first conceived in 1996 by Bonnier, DeMello and Lipton in a very popular attack on RSA. Later on, Beham actually developed the differential fault analysis attack on the block cipher DES, and also there were other different types of fault attacks like the optical fault induction attacks by Anderson, which was published in Chess 2002. So, the basic idea of a fault attack is something like this. The assumption is that the attacker has in possession a device. Now, this device for the attacker is like a black box. Internally, it has an encryption algorithm which is stored inside the device. Now, the attacker is able to send messages which we call as plain text, trigger this encryption algorithm to execute, and also collect the ciphertext. The objective of the attacker is to somehow extract the secret key which is stored inside the device. So, what the attacker would do is that first of all he would fabricate some particular message and pass it to the device and force the device to create an encryption. So, the encryption would the message would pass through the encryption algorithm which is implemented in the device, and it would give you a ciphertext. We call this particular ciphertext as a fault free ciphertext. Next, what the attacker does is that he sends the same message, the same plain text, through the same encryption algorithm in the device, but this time as the device is encrypting that particular message, the attacker would induce a fault in the execution. What the fault would do is that it would toggle a few bits during the computation, or it would skip a few instructions, or it would manipulate what operation is being executed during the execution. As a result of this error or this fault that is induced, the ciphertext that is obtained would be incorrect. Thus, the attacker would have a faulty ciphertext which looks different from the original fault free ciphertext. So, we have two ciphertext, a fault free ciphertext and a faulty ciphertext, and both these ciphertexts are essentially different. Now, the attacker would analyze the fault free ciphertext and the faulty ciphertext, and from this derive the secret key. So, there are essentially two things to look over here. First is how would the attacker induce the fault during an encryption, and secondly, how would the attacker identify from the faulty ciphertext and the fault free ciphertext what the secret key is. In order to actually inject the fault, there have been several ways proposed in the literature. Some of them are extremely cheap, and you could actually be able to do it with less than $1,000, while other techniques for fault injection are much more expensive. So, the expensive ways would look something like this, where we would have a laser. So, we would place the device which the attacker is interested in the laser and fire a laser at this specific device. Now, this laser, when it is pointed to a specific to the device, would toggle some bits during the computation of the cipher and thus induce the fault. Similarly, a fault can also be induced by injecting glitches in the power consumption or by having a glitch in the clock source for that specific device. So, what happens when we have a glitch in the power consumption is that this glitch or this glitch can again toggle the device state, resulting in a wrong or faulty computation. Similarly, a glitch in the clock source for the device can create a setup or a hold violation, injecting a fault into the operation of that device. There are other techniques which also have been experimented with, such as the use of temperature. Increasing the temperature of a device, as we know, would cause or would induce faults in the device. However, as the experiments show, injecting faults using temperature is more difficult to achieve compared to the other techniques of power glitching or clock glitching. So, this is an example of fault injection using clock glitching. So, what we have here is an AES implementation. Now, this AES implementation takes a plain text and the secret key and gives you a cipher text. Now, this AES implementation also takes as input a clock source as well as a reset signal. Now, in order to induce a fault at a specific time during the execution of this AES, what we do is we have a multiplexer which multiplexes between a slow clock and a fast clock. So, whenever an attacker wants to induce a fault, he would change the value of this select line for this multiplexer from 0 to 1 and thereby inducing a fault. So, what would typically happen in the normal operation of this device is that we would have a slow clock which is passed through. So, this means that the select line for this multiplexer is 0, and therefore, you would have a slow clock passing to this, and AES is operational on a slow clock. Now, when the attacker switches to 1, so momentarily we would have a fast clock that is pushed into the AES clock input, and momentarily the AES is functioning at a very high rate using the fast clock. So, this fast clock violates setup and hold times of various gates in this AES circuit, resulting in a faulty output. Now, this faulty output then propagates to the output of this AES hardware, resulting in a faulty ciphertext. So, this particular figure over here shows the effect of a fault. So, if you highlight on this particular area, we see that it has a value of 282.9E. So, this is the result when there is no fault which is when present. Now, if we just inject a fault due to things like clock glitching, what we see is that this value of 282 gets modified to 292. So, what we observe here is that one bit has actually toggled. So, instead of a 8 over here, it has become a 9, indicating that the LSB bit of this particular nibble has actually been modified, and this modification has occurred due to the fault that has been induced. So, there are various different types of fault models. The most common one is the bit fault model. So, we have seen a bit fault model over here, where exactly one single bit has been modified. A bit fault model, as an example, is seen over here. You have a state in the cipher which has a value 8823124345. In the bit fault model, we assume that the attacker is very precisely be able to inject a fault. Rather, one byte over here has just been modified by a single bit. So, for instance, over here 23 has now become 33. That is one bit that has modified the state of the cipher. So, we call this as a bit fault model. Another fault model is known as the byte fault model. Here what we assume is that one byte in this entire state has been modified. So, we have like 8823124345, which has changed to 8836124345. Essentially, this 23 has become 36. So, the assumption here is that within this specific byte of 23, it could change to any of the other 255 different values, but the other bytes like 88, 12, 43 and 45 and not affected by the fault. A third fault model, which is the most practical of all, is the multiple byte model. Here we see that the fault is not restricted to a single byte, but rather it could actually spread to more than one bytes. So, in this particular example, what we see is that 23 has become 36. Similarly, 45 has changed to 33 due to this multiple faults. These fault models actually influence the complexity and power of the attacker. Now, if an attacker is able to inject a bit fault, that is precisely change exactly one bit in the fault, then the attack becomes extremely easy. On the other hand, actually injecting such a bit fault is extremely difficult in practice. On the other hand, injecting multiple byte faults is much far more easier, and the attacker would be able to inject such multiple byte faults far more easily. However, extracting secret information using a multiple byte fault is more difficult. What we see over here is that as we move from the multi-byte fault to a bit fault model, the attack becomes much more easy. On the other hand, the practicality of the attack starts to reduce. So, attacks which use the multiple byte model is more practical compared to the attacks which use bit fault model. This is due to the fact that it's easier to inject faults in multiple bytes than to inject faults in precisely one single bit. So, let us take a look at a popular fault attack on the RSA public key cipher. Now, the RSA decryption works like this. So, we have Y, which is the cipher text, and we raise it to a secret key known as A. So, Y to the A modulus n would give you the plain text X. Typically, the value of A would be quite large, it would be around 1024 bit. Decryption, which is done with an exponentiation algorithm, would then give you a value of X. Now, let us look at a particular and a very simple fault attack, where an attacker could determine one bit of A, that is one bit of the private key A. Now, what the attacker would do is he would first consider a bit fault model, where during the execution of this RSA decryption, he forces one bit of A to go from 0 to 1, right. So, that means if the bit of A is 0, then he would inject a bit fault and change that particular bit to 1. On the other hand, if the value of A in that ith bit was 1, the attacker's fault would force the value of A to go to 0. Let us say that the value of A is equal to say 0, 1, 1, 0, and the ith bit we will take I to be having a value of 2. So, we are considering the bit fault model, and therefore, the attacker targets this specific bit. For example, he would focus his laser beam on this bit and change this bit from a value of 1 to a faulty value of 0. So, this is the faulty value of A. Note that the attacker does not know the value of A, because A is actually embedded into the device, but rather he somehow has figured out how to inject a fault that could potentially change this bit. So, without knowing the bit, what the value of the bit is, the attacker has somehow injected a fault to toggle the ith value of this bit. So, we have taken this particular example where A, which is secret, has a value of 0, 1, 1, 0, and the attacker has somehow, due to the fault injection, changed the value of A to 0, 0, 1, 0. Now, the decryption goes on as normal. Now, when the fault is not injected, X would have the value Y to the power of 0, 1, 1, 0, this is the base 2 mod n, while in the case when the fault is injected, he would get a wrong value, which we denote as this, which is y to the power of 0, 0, 1, 0 to base 2 mod n. So, what we identify is that the value of x and x tilde is going to be different. Now, what the attacker has in his position are these two values, x and x tilde. From this, he needs to identify that the original value for this ith bit should be 1. In order to do so, the first thing we observe is that if we subtract a and a tilde, a minus a tilde, we would get 6 minus 2, which is essentially plus 4. On the other hand, let us say that a had a value of 2 injecting a fault. So, this was one condition, and we are now assuming that a has a value of 2 and injecting a fault in the I equal to 2 location. The attacker has somehow been able to change a to 6 like this. Now, in this particular case, he would have obtained a minus a tilde to be 2 minus 6 to be equal to minus 4, right. So, what you see here is that a minus a tilde is either equal to plus 2 to the power of I, where I is 2 in this case, or minus 2 to the power of I. So, you see that depending on whether the original value was 1 or 0, you would get either a positive value of 2 to the power of I or a negative value of 2 to the power of I. However, what the attacker only has is x and the x tilde. So, how does he obtain this difference 2 of I or minus 2 of I? So, in order to do this, what he does is he takes x and he divides it by x tilde as follows. So, you have x and divides it by x tilde. So, essentially you would get y to the power of a mod n divided by y a tilde mod n. This is nothing but y a minus a tilde mod n, right. So, this is essentially either y to the power of I mod n if the ith bit over here had a value of 1, or he would get the value of y minus 2 to the power of I mod n. So, you see that dividing x and x tilde would either give him a value of y to the power of I mod n or y power minus 2 I power I mod n. So, since the attacker also knows the value of y, that is a cipher text, he can pre-compute what the value of y 2 to the power of I mod n as well as y minus 2 power of I mod n, and given x and x tilde, he can determine whether it was either this case or this case, and thus infer whether the ith bit was 1 or a 0. With this way, the attacker would obtain 1 bit of the secret key. Similarly, by injecting faults in every other bit, the attacker can slowly be able to recover every bit of the secret key. So, what we see over here is that this attack is extremely easy to do, provided that the attacker is precisely able to inject 1 bit fault in the secret key of the RSA. So, looking at the practicality of this attack, it is not going to be that easy, because injecting a bit false is first of all difficult, and in this particular case the attacker would need to inject a large number of false. So, if the key size is say 1024 bit, he would need to inject 1024 bit false in order to fully recover the secret key. So, there have been many further attacks on RSA. So, many further fault attacks on RSA which have been much more efficient and which were able to more efficiently get the secret key extracted from the RSA device, but we will not go into those details. And I would leave it to the interested readers to actually look at the papers that follow this and look at the various attacks. Thank you.